Welcome to Mr. Brown's Basement, a channel devoted to sharing the craft of repairing, restoring, and modifying vintage electronic gear, and other random stuff.
Welcome back to Mr. Brown's Basement. Today we're going to be looking at a Geiger counter from the early 1960s. What it's used for is to detect atomic radiation, and it uses an old-style Geiger tube, which is this thing that comes off. It comes off a lot easier when you're not holding a camera. Hold on. It comes off much more easily when you have a free hand. Anyway, this is the probe, and it contains a gas-filled tube. And the gas-filled tube is connected up to a high-voltage power supply. Normally, the tube doesn't conduct, but under the right conditions, for example, when a high-energy particle wanders through the tube, gas is ionized and conducts just for a moment and gives you a click in the headphones, or it gives you a reading on the meter. And the amount of radiation is measured in the number of counts per minute, though there are different methods used now. It's not a complex instrument, but there will be a few challenges when repairing this one. Mine is made by Anton, though other companies made them too. Victorine and Universal come to mind. And each model and each manufacturer had their own schematic and slightly different way of doing things. This video will be specifically about my Anton CD V-700 No.6. And I went to the internet and found a schematic for it. Here's the schematic. The circuit can be divided into two parts. We've got this part over here, which is an oscillator and a step-up transformer, and a shunt regulator, V5. It's a gas-filled tube, and that leads to the actual Geiger tube itself. They call it GM tube. The second part of the circuit is the part that translates the momentary conduction to a click. So you have a transistor and a wave shaping network, a meter, and ultimately, right there, an output transformer to a set of headphones. There are a number of challenges that come with repairing this. First of all the old capacitors will have to go. There aren't that many. It's a simple recap job. The other challenge is the transistors. Sometimes germanium transistors don't survive the test of time and need to be replaced, and germanium transistors are scarce, so you might want to get a few of them just in case. The last thing is the shunt regulator. This V5. It's a special tube, I don't recall the name of it, but it's filled with gas and actually some radioactive material, and they go bad because the radioactive material has decayed. It regulates the voltage to about 920 volts from the transformer. Without it, it would be much higher, but it has to be in a sweet range which prepares the Geiger tube to conduct when a particle runs through it, but not so high that it's conducting all the time. We need a regulator that is going to do the job of that tube, V5. When you think of shunt regulators, you think of Zener diodes, and that's a great idea, except there are no Zener diodes that operate at 920 volts. But we can cheat by putting a bunch of Zener diodes in series. That will act as one big high-voltage Zener diode. Now that's an overview of the circuit and what we're going to have to do. Let's actually take a look at the unit. Well, here's the unit. It's held together with a couple of catches. And inside reveals the guts. It takes 5 batteries. I think 3 of them are for the high voltage and 2 are for the headphones and the meter. This is going to take a little bit of cleaning. Inside, that's the voltage regulator tube. It's called a Chorotron. It contained some isotope of radium. It's decayed. I think it has a half-life of about 20 years. So this was made almost 60 years ago. It will be mostly decayed, about 80% decayed, so it's useless. It won't regulate as it's supposed to. Here are the Zener diodes. These came off eBay. 1N5883B. I also got some of the same, or almost the same, from DigiKey. It says 150 volt. Well, if they are 10% high or 10% low, that's going to be too much. So what we're going to do is we're going to have to measure the Zener voltage of each one that we need, and then we can cobble them together and have the Zener voltage we want. I also bought some lower voltage Zener diodes, which will be much easier to test. Again, from DigiKey, for example, these 1N5355. I can use them. That's an 18 volt Zener diode. So if I have, let's say, exactly 900 volts, I can trim it to almost 920 using one of these. It actually can be 920 plus or minus about 5%, but don't want to go much higher or too much lower because it just won't work. To test 150 volt Zener diode, we need a power supply more than 150 volts. And that can be dangerous. I don't want to use mains. I've got a better solution. And it's thanks to Mr. and Mrs. eBay. It's this. This is a small DC to DC power supply. And it's about 10 volts in. I think 10 to 40 volts in, actually. And a couple hundred volts out, which is fine. I think this was about $10 or something on eBay. Something like that. So what we're going to do is we're going to hook up a little circuit, and I'll put the diagram up on the screen, and then we will determine the Zener voltage of the diodes. We'll have a regulator that works and gives us the voltage that we need. Just one thing about a couple hundred volts. This thing probably won't kill anybody, but it can still give you a nasty shock. And if you have some health condition like pacemaker, probably a good idea to avoid getting a shock from this. Here's the circuit we're going to use to test the Zener diodes. We've got VN, 10 to 40 volts, though we could probably get by with closer to 10 volts. We should get around 200 volts out, which is fine. A 1 mega ohm resistor, which limits the current through the diode, and it is going to be reverse biased. That's how Zener diodes work. Whatever is left across the diode is what we're interested in. This is going to limit the current to about 300 microamps. Now these are 5-watt diodes. I suppose I could have got smaller ones, but remember we're dealing with fairly high voltage, and at a high voltage even a little bit of current works out to be a reasonable amount of wattage. 5 watts is plenty. Once I make sure I have at least 200 volts here, I'm going to connect up this circuit and see what I'm getting here. For the purpose of testing it, I've got black and red for negative and positive, and I'm going to be using exactly 10 volts. For the output, I've got green for negative and yellow for positive. To my meter, I've got it on the highest, and that's the 600 volt range. Then we'll see what the open circuit voltage is. If it's not right, you can use a small jeweler's screwdriver and adjust the trimmer and get something in the range we want. So I'd say 200 volts is good if we're going to be testing a 150 or 200 volts Zener diode, as long as it's through a resistor. But we're not there yet. So let's turn it on and see what happens. Okay. And guess what? 133 volts. Not too bad. Okay, I don't want to touch anything. So I'm going to adjust the trimmer and see what happens to the voltage. It's a 10 turn, and I could be turning for a while. No, I think 10 volts is not enough. I'm going to increase it. Oh, it's gone down to 9.5. Okay. Let's see what happens here. So I got my screwdriver on the trimmer. Let's see what we can do here. Yeah, that's looking good. As long as I don't reach the end of the trimmer. 170, 180. Oh, I think I've reached the maximum. 184 volts. Okay, well, I guess I'll go for a little bit more. "180 volts isn't exactly as high as I wanted. I can't test 180 volt Zeners with this, but I certainly can test 150 volt Zeners with this. Okay. Not exactly what I had in mind, but I can manage. I've put a 1 mega ohm resistor right there, brown, black, green, plus or minus 5%, and I did check, it's about 5%, in series, and I'm getting 165.5 volts, where it was about 180 before, and that's because with a mega ohm in series, this is actually close to the internal resistance of the voltmeter. There's an appreciable voltage drop across it. And that's okay. We know it's at least 150 volts, and we're testing 150 volt Zeners. So this is the open circuit with the 1 meg. Okay, I'm going to test the first Zener diode. I'm just going to put it across the meter, and it goes down to 152.3 volts. So we'll call it 152. Not bad. I can manage that. 6 of those. Gives me very close to 920. I've labeled the first diode, 152.3. And here we're going to test the next one, which is, let's say 153.5. That's good. So I'll test a bunch of them. I don't have to do it on camera. Without going much further, I gotta say I'm very impressed. These Zener diodes are all within 1 or 2%, and usually they would have to be within 5%, but they're within, let's say, 2% would be 3 volts. None of them is at well, there's the highest one, 153.6. So that's just a little bit more than 2%. But we've got this one over here, which is within 1%. So I'm really impressed. I'm not going to test all the Zener diodes. I only have 50. But I'm not going to test them. They're all within the range. So I'm going to put 6 of these in series. It's going to give me just a little bit more than 900 volts. 920 is the target, but you actually can be a little bit above or a little bit below. With these diodes in series, I've got a Zener voltage of just under 913 volts, which is nothing to whine about. I suppose I could get a 6 volt Zener diode and bring it up to 918, but honestly, this is quite reasonable. So what I'm going to do is I'm going to leave it with these 6 Zener diodes in series. I'm not going to deal with it yet, but my plan is to solder them together into a bundle and make sure they are well insulated with heat shrink, and use those in place. Hopefully they're not much bigger than the original Chorotron tube. Looks like there are 1, 2, 3, 4 screws that hold on the rusty battery holder, and they go into standoffs, so that'll be first. Those 4 screws are removed, and not too surprisingly, one of the battery contacts was so corroded that it just fell off. Better to know about that now than learn about it later on, so it's not the end of the world. I'll find some way to reattach it after I've cleaned it up. That's, you can tell there were batteries in here that probably should not have stayed in here that long, but that's what batteries did back then. And there's the next level. We've got a couple of capacitors here and here. The Chorotron. Now, I've thought long and hard about that, how I'm going to dispose of it. But it shouldn't be a problem because all the radioactive material has decayed. So I can probably take it to e-waste. It should be essentially lead inside. So, and there wasn't that much radioactive material in there to begin with. There's the one of the transformers. So this board is mounted on the switch. So I'm probably going to have to take out the selector switch from on top to get the rest of this out. The printed circuit is held in by the knob. And the knob is held in by a pair of screws, grub screws or slugs. And this didn't want to come off, so I added some lubricant, and now it's really loose. But I had to let it sit overnight. The shaft may not want to come out of the hole. That's because it's a really tight fit. So grab it with a pair of needle nose pliers and gradually wiggle it out. It will come out, but as I said, very tight fit. I'm thinking to make this easier to deal with, I'm going to disconnect the battery container by desoldering and of course labeling the 4 wires, and maybe instead of using this battery container that accepts D cells, maybe use one that accepts AAs because well, they're cheaper, and an AA alkaline probably has more capacity than an old carbon zinc D cell, especially one from the early 1960s. Here's a view of the component side of the printed circuit. Some components look a little different. They did way back when. This is a meter rectifier. It's probably just a germanium diode, and it's probably okay. This is rather important here. That's a high voltage rectifier. I'm guessing it's probably selenium, but I don't know. Could be silicon. Whatever it is, it needs to be tested. All these resistors need to be tested. There's a capacitor, another capacitor. This is an electrolytic capacitor. That's the 3 volt 200 microfarad capacitor. There's the high voltage transformer and the output transformer. And there's 1, 2, 3 germanium transistors visible here. There are some disc capacitors that are probably fine. I believe this is a thermistor. And other than that, not too much excitement, no surprises. Here's the parts list for capacitors in my Anton Geiger counter. It's worth mentioning that if you have a different Geiger counter, one made by Victorine or by Universal, or a different version of this one, the parts list will be different and the schematic will be different, perhaps very different. Please do consult the right schematic and the right parts list, and don't use this one unless you have exactly this Geiger counter. One capacitor here, which would have been difficult to replace because I don't normally stock that size. I'm in luck. That's a ceramic. You don't replace ceramics. You only replace paper capacitors and electrolytic capacitors because they both deteriorate over time. I don't have an axial capacitor in this size. I only have a radial one. Same thing, just a different package. Axial capacitors aren't made in the same numbers anymore, so they're harder to come by and far more expensive. I was curious exactly how much radiation might be coming from that old tube, so I got out another Geiger counter. Right here, as I'm standing in Mr. Brown's basement, I'm getting 0.11 microsieverts per hour, which is normal background radiation. So let me take the probe and bring it close to, down a little bit, bring it close to the Chorotron and see how much radiation is coming from there. Well, at least in the radiation that this Geiger counter measures, it's the same as the background radiation, down to 0.09, 0.1 microsieverts per hour. So really, this is not radioactive at all. Here's a close-up look at the Chorotron. It's labeled Anton Labs 6102 and 416 or 41G, I can't tell. And as you see, it's clearly labeled as radioactive, though it isn't anymore, at least not as far as I can tell. And I will check again, just because I'm curious. I've now replaced the capacitors that need to be replaced. And I tested the resistors that could be tested in circuit and pulled a leg out of those that could not. And I found a grand total of 2. That's 2 out of 14, or 2 out of 12 resistors that were out of tolerance. And they weren't even that far out of tolerance. Except there's one resistor I can't check. And that's a 6.8 mega ohm, because my meters don't go that high. So I'm going to have to assume it's okay. Here is my replacement voltage regulator. There are 6 diodes wired in series, and they've been triple insulated with heat shrink. I think the breakdown voltage for heat shrink is around 600 volts. So this should be good to about 1800, though it should never see 1800 volts ever. Just to be clear, this is the original circuit. The high voltage winding of T2 goes through rectifier CR2 and is smoothed out by C7. Then it goes to shunt regulator, the Chorotron tube, and that's through a resistor R14, I think 6.8 megs, and then positive goes to the Geiger tube. We're now changing that to exactly the same thing, except instead of the Chorotron tube, there's now a Zener diode, which I've shown as one very sick-looking Zener diode, but it's actually 6 in a row with a Zener voltage of around 912 volts, or whatever it is. These are the parts that were replaced. 4 paper capacitors, 1 electrolytic capacitor, 2 resistors, and 1 Chorotron tube. That was it. Zener diodes have been installed, and what I'd like to do is just power up the high voltage part of the circuit to see if I can measure, let's say, about 900 volts across the Zener diodes. What I'll do is I'll bring up the voltage slowly and just see what it's doing. Now that part of the circuit uses 3 volts, probably at a fair amount of current, so I'll use my variable power supply to get that. Voltmeter hooked up to the high voltage, and my power supply, which is off right now but set at 1.5 volts to start, to see what happens. What's a little bit weird is that if you look at the circuit, on the low voltage side, it's actually a positive ground. The ground of the circuit is right there, and that's connecting to the positive of the 3-volt battery. And that's because they're using PNP transistors, and they're sort of counterintuitive, but the emitter is positive, not the emitter being negative, but that's what was available back then. So let's see what happens. 0 volts. Hit the power. 1 volt. 1.9 volts. 2 volts. 40 milliamps. 2.3 volts. 2.4 volts. 2.3 volts. I'm getting only 67 volts on this range. Well, hard to say. And I have a feeling it's because I'm measuring this side of the 6.8 mega ohm resistor. So my meter is probably a significant load. So I'm going to change that and move it to the other side of the resistor and hopefully get a better reading. Okay, let's try this again. 2.3 volts, here we go. Okay. Okay, seems to be quite sensitive to input voltage. 2.8, 2.9, at 100 volts. I find that very hard to believe. That I'm only getting 100 volts. Now it's very possible that this circuit is capable of very, very little current. Wow, I've never used this camera with a scope before. Well, with 10 volts per division, I've got a waveform about 10 volts and around, well, time base is 1 millisecond per centimeter. Got about 5 centimeters between pulses, so about 200 hertz. And that's a fair waveform. I would guess that it's doing what it's supposed to be doing. That's based on 3 volts going in. I'm going to have to conclude that my meter's sensitivity is just too low and that something is happening. must be getting high voltage, certainly more than 100 volts. The oscillator is certainly running. I can hear it. I don't know for sure whether it's in the target range, but I certainly have every reason to believe it is. So let's get the thing back together. I've put it all back together. My solution for the corroded battery container is to use 2 small battery containers, two AA cell for the high voltage supply and one 3 AA cell for the audio and meter circuit. Here's my solution for the bottom. The 2 battery holders are just resting in place, clamped in by a piece of mending strip or metal strapping, whatever you want to call it. This stuff. They're not going to go anywhere. And if I use alkalines, that should give me plenty of life. What I may do in a future video is come up with a clever way to get some sound out of it without speakers. But that will be for another day. Use the headphones. You need a very high impedance headphone, something like 2,000 to 4,000 ohms, and I just don't have one. And I did measure the output. It's fairly low, so it's not like it can power anything else like a small speaker. So what I might do in the future, unfortunately it's not a very nice standard connector, it was standard 50 or 60 years ago, I might put together a high impedance amplifier like an op-amp driving a speaker, and that will allow me to hear the ticks. Now let's actually test it and see what it says. I've got 2 AA's in there. I don't have enough AA's on hand to fill that battery holder, so I'm going to use my power supply, which is set at 4.5 volts. And let's turn it on. I don't have any headphones, but I do have an amplifier, or amplified speakers. And I've connected them up to the phone's jack, and when you hear a tick like that, that's the sound that you get from a Geiger counter. And here's that tube. Nothing from that tube, just background radiation. Apparently bananas are a little radioactive. I don't have any bananas. So I guess that's all for today. I hope you enjoyed this video. And if you did, please consider giving it a thumbs up. Perhaps consider subscribing to this channel for more interesting and unusual videos. Thanks again for watching.